Atmosphere. We breathe oxygen and breathe out carbon dioxide. Without oxygen, we can't live. Green plants take in carbon dioxide, use sunlight and water to photosynthesis, and we end up getting delicious fruits, vegetables, grains, etc. The atmosphere is a sea of gases surrounding Earth. When we compare the size of the Earth, the atmosphere is a thin blanket surrounding Earth. The atmosphere is about 1000 kilometers thick. The National Aeronautics and Space Administration (NASA) gives this description. If Earth is the size of a basketball, the atmosphere would be like a thin sheet of plastic wrapped around it. There are many gases in the atmosphere, but oxygen, about 21% by volume, and nitrogen, about 78% volume, dominate.
Earth's atmosphere. The atmosphere is made up of a mixture of gases, mostly oxygen and nitrogen, that wrap around the Earth like a blanket. The air of our planet is 79% nitrogen and just under 21% oxygen. The small amount remaining is composed of carbon dioxide and other gases. Without the atmosphere, we will not be able to live here. Those gases protect us by blocking out dangerous rays from the sun and making Earth a perfect habitat for plants and animals. The Earth's atmosphere has 5 layers: troposphere, stratosphere, mesosphere, thermosphere, and exosphere. Atmospheric gases become thinner as you go higher. The troposphere is the lowest layer of the atmosphere. It begins at the surface and extends to between 7 kilometers, 23,000 feet at the poles and 17 kilometers, 60,000 feet at the equator, with some variation due to weather factors. This part of the atmosphere is the most dense. As you climb higher in this layer, the temperature drops from about 17 to minus 52 degrees Celsius. The troposphere is known as the weather layer since snow, wind, and rain stick to this layer. The stratosphere starts just above the troposphere and extends to 50 kilometers, 31 miles high. Compared to the troposphere, this part of the atmosphere is dry and less dense. The temperature in this region increases gradually to minus 3 degrees Celsius due to the absorption of ultraviolet radiation. The ozone layer, which absorbs and scatters the solar ultraviolet radiation, is in this layer. 99% of air is located in the troposphere and stratosphere. The mesosphere starts just above the stratosphere and extends to 85 kilometers, which is 53 miles high. In this region, the temperatures again fall as low as minus 93 degrees Celsius as you increase in altitude. The chemicals are in an excited state as they absorb energy from the sun. This is also where most meteors burn up when entering the atmosphere. The thermosphere starts just above the mesosphere and extends to 600 kilometers, 372 miles high. The temperatures go up as you increase in altitude due to the sun's energy. Temperatures in this region can go as high as 1,727 degrees Celsius. Chemical reactions occur much faster here than on the surface of the Earth. This layer is known as the upper atmosphere. The thermosphere also includes the ionosphere, a region which is filled with charged particles. The exosphere starts 500 kilometers above the Earth and is the highest layer. It starts at the top to the thermosphere and continues until it merges with the interplanetary gases or space. In this region of the atmosphere, hydrogen and helium are the prime components and are only present at extremely low densities.
Other gases are in a very small percentages. These includes argon, neon, carbon dioxide, methane, ammonia, ozone, etc. Water vapor accounts for about 0.4% by volume over the whole atmosphere. Water vapor is a gas? No, the clouds that you see in the sky are not water vapor, they are water droplets. Apart from these gases, the atmosphere also has fine dust particles which are called particulates. Structure of the atmosphere. Just like the interior of the Earth is arranged as layers, atmosphere too is arranged into various layers having different compositions. On the basis of chemical composition, the atmosphere is divided into two broad layers. 1. Homosphere, 2. Heterosphere. Homosphere. The homosphere extends up to a height of 90 kilometers. It consists 3 layers: troposphere, stratosphere, mesosphere. It is characterized by uniformity in composition of gases like nitrogen, oxygen, argon, and carbon dioxide. Troposphere. The troposphere is the lowermost layers of the atmosphere. Its average height is 13 kilometers and extends roughly to a height of 8 kilometers near the poles and about 18 kilometers at the equator. It contains about 75% of the total gaseous mass of the atmosphere, and particularly all the moisture and dust particles. Condensation, evaporation, perspiration, rainfall, cyclones, etc. occur in this layer. Stratosphere. This layer extends up to a height of 50 kilometers. This layer is almost free from clouds and associated weather phenomenon, making conditions most ideal for flying jet aircrafts. One most important feature of stratosphere is that it contains ozone layer. The temperature increases as there is increase in altitude. Mesosphere. It extends up to a height of 80 kilometers. Meteorites burn up in this layer on entering from the space. Temperature starts decreasing with the increase in altitude. Heterosphere. The layer above 90 kilometers of the atmosphere is called heterosphere. It has a heterogeneous composition and hence the name heterosphere. It has 2 layers: 1. Thermosphere, 2. Exosphere. Thermosphere. It extends up to 400 kilometers. In thermosphere, temperature rises rapidly with the increase in height. It contains electrically charged particles known as ions. Radio waves transmitted from the Earth and reflected back to the Earth by these ions. It is also known as ionosphere. Exosphere. It is the uppermost layer of the atmosphere. This is the highest layer and very little is known about it. Pressure belts and planetary winds. Air pressure. The air around us is composed of gas molecules. These molecules are constantly pushing each other or any object that comes their way. Thus, air exerts pressure not only from the top but also from the bottom and the sides of an object if it is exposed to air on those sides. When gas molecules heat it up, they get a lot of energy and start moving very fast. When heated air rises, it starts losing the energy that it got from Earth's surface. When the energy decreases, the molecules slow down, become more sluggish and get closer to each other. Air becomes cooler and denser. Dense air starts falling back towards Earth's surface due to gravity. When any part of the Earth heats up and causes low pressure, it means that there is more vacant space and less molecules. That is why we say that wind flows from high pressure areas to low pressure areas.
Heliophysics is the study of the Sun and its interactions with the Earth and the solar system. The Earth's atmosphere has 4 primary layers. The lowest is the troposphere, then the stratosphere, mesosphere, and thermosphere. These layers, particularly the upper 3 and the existence of ozone in the stratosphere, protect our planet by absorbing harmful ultraviolet radiation. NASA scientists use balloons to collect in situ measurements of the atmosphere. Sounding rockets are used to collect more detailed data in the mesosphere and the thermosphere, both of which are too high for balloons. Satellites are also used to gather measurements of the upper atmosphere. NASA's Aeronomy of Ice in the Mesosphere AIM satellite remotely senses unique night-shining clouds made of ice crystals at an altitude too high for water vapor clouds. These noctilucent clouds form over the summer poles and vary in brightness throughout the year. Satellite data reveal a trend of increasing brightness of noctilucent clouds over the past few decades. Since the mesosphere is responsive to small changes in atmospheric chemistry and temperature, noctilucent clouds may provide clues to the interaction between natural and human-caused changes in the atmosphere. In 2011, observations show dramatically lower ice content above the southern pole, caused by a pulse of warm air in the upper atmosphere. NASA scientists theorize that these warm temperatures were triggered by changing weather conditions in the northern or opposite hemisphere. Researchers hope noctilucent cloud data will contribute to the understanding of how the sun's cycle affects the Earth's atmosphere and pole-to-pole atmospheric circulation. Higher altitude does not necessarily mean colder temperatures, because temperature does not change consistently through the layers of the atmosphere. Temperature decreases with altitude through the troposphere, but then increases through the stratosphere. Conversely, the temperature decreases in the mesosphere, and it contains some of the coldest temperatures in the atmosphere. The thermosphere then begins to warm with higher altitude. The thermosphere warms because molecules of oxygen and nitrogen move faster at this altitude and are bombarded by radiation and energetic particles from the sun, causing the molecules to split into their component atoms. Both the speed of the molecules and splitting of the atoms create heat. The atomic oxygen and nitrogen cannot radiate the heat from this absorption, causing the thermosphere to reach temperatures as high as 2,000 degrees Celsius. As the Earth rotates, the thermosphere is exposed to highly energetic ultraviolet and X-ray solar radiation that ionize the atomic oxygen and nitrogen in the thermosphere. These charged atoms form a layer of plasma called the ionosphere. The ionization of atoms can extend down as far as the mesosphere. However, these upper atmospheric layers are still mostly neutral, with only 1 in a million particles becoming charged daily. The density of this ionosphere layer cycles daily. At night, the ionosphere diminishes as the sun's radiation ceases to interact with the atoms in the thermosphere. However, there are still small amounts of charged atoms caused by cosmic radiation at night. A unique property of this ionized atmospheric layer is that it reflects shortwave radio waves, enabling communication over great distances by bouncing signals off the ionosphere. However, variability of the ionosphere can disrupt communication. Solar storms is one such variable that can enhance this layer, even shutting down communication between ground stations and satellites. Solar storms can also send highly energetic particles, mostly electrons, along Earth's magnetic field lines into the upper atmosphere at the poles. Here, they interact with oxygen and nitrogen, causing formation of auroras. Auroras are formed when an energetic electron strikes an atom and one of the atom's electrons jumps to a higher energy level. When the electron returns to a lower energy level, energy is released, often in the visible light region of the electromagnetic spectrum. A deep red aurora is caused by the excitation of nitrogen atoms. Excited oxygen atoms create a green aurora at lower altitudes and a red aurora at high altitudes. A small amount of solar particles constantly precipitate from the magnetosphere, forming a background aurora that can be seen from space. NASA's AIM and Themis missions have provided valuable information about Earth's upper atmosphere. NASA's RBSP and MMS missions study the interactions at the upper atmosphere and the magnetosphere from space weather effects.
Pressure belts. The Earth's surface does not heat uniformly. Land heats up faster than sea. Land deep island heats up faster than land near the sea. Water takes more time to heat, so the air above water gets heated more slowly. So the heating and cooling is happening at different rates in different places. The tropical latitudes receives the most intense amount of solar radiation are hotter than temperate or polar latitudes that receive less intense solar radiation. Hence, the tropics are hotter than the rest of the world. So, with temperature variation, there is pressure variation around the world. When air moves from areas of higher pressure to areas of lower pressure, we call it wind. If it moves at a very slow pace and we feel comfortable in it, we call it breeze. If the wind comes in a short and fast burst, we call it gust. If wind moves very fast and blows things around, we call it storm. Winds are moving all over the world. At the equator, the high temperature heats up the atmosphere and the hot air rises, creating lower pressure at the Earth's surface around the equator. This low pressure belt is called equatorial low pressure belt or the intertropical convergence zone. As it reaches the upper heights of the atmosphere, the air spreads away from the equatorial region towards the northern and southern hemisphere. Where it descends, we find the pressure is higher, is called subtropical high pressure belt. The air in the areas of the North Pole and South Pole are so cold that the air there is at higher pressure than the area of latitudes along the Arctic and Antarctic Circle. Normally, we would have expected the winds to move in a straight line from north to south or south to north from the temperate zone to the tropic zone. But actually, the winds move slightly to the right in the northern hemisphere and to the left in the southern hemisphere. This is because of the impact of Earth's rotation on its own axis. This effect is called Coriolis effect. The winds play a very important role in the weather and climate patterns around the world. They have also played a very important role in the history, like Vasco da Gama found the sea route India using winds to power his ships. He was able to transport and trade large quantities of pepper, cinnamon, etc. to Portugal. In this way, these winds also were crucial to the establishment of Portuguese rule over Goa. Classification of winds. Depending upon the wind speed, their features, their directions, the way they occur, winds are classified into three types. Planetary winds, occurring on the planet as a whole throughout the year. Seasonal winds, restricted to regions or seasonal in character. Local winds, local in character. Planetary winds. The winds that blow continuously and regularly above the world pressure belt are known as planetary winds. The winds moving in direction from east to west are known as northeast trades in northern hemisphere and southeast trades in southern hemisphere. Westerlies, on the other hand, blow from west to east. That's why they are called westerlies. They are the southwest in northern hemisphere and northern hemisphere and northwest in southern hemisphere. Effects of planetary winds. These winds play a crucial role of transporting heat and moisture across the world. There be no atmosphere, it would have got intolerably hot in daytime or in the tropics and intolerably cold in night or in the polar regions. These winds do not distribute heat or moisture uniformly, which is why we have some parts of the earth quite hot and some parts cooler and some parts with high rainfall and some which are deserts. Seasonal winds. The rainfall which occurs in India is mainly due to seasonal winds. All factors in the country are related to monsoons. It is derived from Arabic word mawsum. Existence of monsoon is due to differential cooling of land and sea. As a result of Coriolis effect, it becomes southwest monsoon over peninsular India and adjacent countries. Local winds. The local winds blow due to local variation in the temperature and pressure and influence a very small area. Hot local winds raise the temperature of the area. Cold local winds sometimes brings the temperature of the affected area below the freezing points. Local winds blow in the lower layer of the troposphere. Mountain and the valley breezes, sea and land breezes are also one class of local winds. Chinook. These winds move down the Rocky Mountains in the USA, Canada and North America. Loo. These are hot and dry winds blowing in the plains of northern India from the west to east in the months of May and June. Mistral. The most famous is the mistral that blows from the Alps over France towards the Mediterranean Sea. Puna. This is the cold local wind in the Andes region. Pamperu. This is the cold local wind in the Andes region. Weather and climate. The state of the atmosphere of an area expressed with respect to sunshine, temperature, barometric pressure, winds, humidity, clouds and perspiration is called weather. It is the average weather condition of a large area on the Earth's surface for a reasonably long period of time. Shimla, being at a higher altitude than Panaji and Delhi, had a cooler temperatures. On the Earth's surface, as you go higher in altitude, the temperature decreases. Humidity and precipitation. Combined with high temperature, it is water vapor that causes you to feel sultry and sweaty. When this happens, we say it is very humid or the humidity is high. The moisture in the atmosphere is derived from water bodies through evaporation and from plants through transpiration. Humidity is the water vapor in the air. In high humidity, our sweat does not cool us because it cannot evaporate. We express humidity not directly but using the concept of relative humidity. It is the ratio between two things: the maximum water vapor that the air can hold at the given temperature and pressure, and the actual amount of water that the air can hold at any given time. Relative humidity decreases with the increase of temperatures and decrease of water vapor. The critical temperature at which saturation level reached is called dew point. Condensation. When the relative humidity exceeds 100%, the excess of water vapor present in the atmosphere gets condensed as minute droplets of water. Condensation can take place only when minute solid particles are present in the atmosphere. Condensation occurs on the outer side of the glass. As moisture in the surface, such as plants, we get dew. The dust particles attract water molecules from the water vapor in the atmosphere. This causes condensation of the vapor into droplets. Cirrus clouds at high level, cumulus clouds at middle level, stratus at lower level, nimbus rain-bearing and vertical clouds. With condensation, the droplets get heavy and fall to earth as perspiration in the form of rain, snow, hail, etc. If these droplets condense very close to Earth's surface, the droplets are lighter and we get fog. Types of rainfall. On basis of origin, rainfall may be classified into three main types: conventional rainfall, orographic rainfall, cyclonic rainfall. Conventional rainfall. This type of rainfall occurs when the moist air over the heated ground becomes warmer than the surrounding air and is forced to raise, expand, cool and yield some of its moisture. Conventional rainfall is common in low altitudes and on summer days in interior part of the continents, and usually come in the form of short heavy showers just after the hottest part of the day, sometimes accompanied by thunder and lightning. Orographic rainfall. Orographic rainfall is also sometimes called orogenic rainfall. We get this term from the Greek oros, meaning mountain. When moist wind is forced to raise over mountain or other elevation in its path, the windward sides of many mountain ranges receives a heavy perspiration, whereas the leeward sides along which the air moves down receives less rainfall. Cyclonic rainfall. This type of rainfall is associated with the passage of a cyclone or a depression. The term cyclone is derived from a Greek word kyklon, meaning revolving. There are two types of cyclones. Tropical cyclone. They are warm core vortex circulation of tropic origin with a small diameter. Temperature cyclone. They occur when the cold, dry, denser air masses converge with warm, wet, lighter air masses.
To understand why the US coastline is so vulnerable to hurricane strike, you have to travel over 4,000 miles east to the place where hurricanes are born. Most hurricanes in the Atlantic begin as very small atmospheric disturbances in the jet stream that flows from east to west over sub-Saharan Africa. Scientists call this disturbance an easterly wave.
One of these waves.
The easterly wave creates a system of turbulent eddies, which go on to develop into a cluster of thunderstorms. These travel west across the African continent, and then encounter the warm tropical waters of the Atlantic.
One begins to see on satellite pictures is these thunderstorms appear to become better oriented each other. The rotation rate increases, the storms become more.
The storm rapidly gathers strength and develops into a hurricane, feeding off the warm, moist air coming from the ocean.
The heat is coming out of the winds, and that's what's powering the storm. When the winds reach typically around 70 miles per hour, the storm may develop a very intense heat and the strongest winds and running.
These are the hurricanes that make landfall in the US every year, causing enormous damage.